This new unit is going to be pretty short and sweet. There's not a whole lot to it. So we're going to start with solving exponential equations, and then we'll also graph exponential functions. And they go pretty well together. They work well together. So let's start with just solving equations. Well, first thing is to know these common perfect squares, cubes, fourths, and fifths. Now, obviously you don't have to have them memorized, but having this table makes things a lot easier because you're going to have to do a lot of base changing, and when you have this table in front of you, it'll help you kind of memorize those bases and common squares, cubes, fourths, fifths, that kind of stuff. So here are some things that you need to know about, first of all, changing the base. Well, we know that in something like this, the 2 is the exponent, okay, and the 8 is the base. So if we want to change this number right here, we want to look in this table and see wherever we find an 8, which this happens to be the only one right here. Well, you'll notice that this is under the x cubed column, and what that means is it is 2 to the third. So what I'm going to do is rewrite this so with a new base. Well, 2 cubed is the same as 8. And so what happens here is when you have an exponent raised to another exponent, you multiply them. So this becomes 2 raised to the 3 times 2, which is 2 to the 6th. And so these are kind of the steps that you would follow in changing the base. And you'll see why you have to know how to change the base here in a minute. When you work with fractions or any negative exponents, here's what you would need to do. So anytime you have a fraction, you want to switch it to have a negative exponent first. So I'm going to go ahead and make this 16 to the negative first power because 16's exponent is 1. So now we have our exponent here and we have our base number. So we actually have a couple options for this base. We have a 16 in this row here as an x to the fourth. So 2 to the fourth is 16. But we also have a 16 down here where 4 squared gives us 16. And so we have two different options. I'm going to show you both of them. The first one would be to replace the 16 and write it as 2 to the fourth. Now again, because you multiply exponents, it becomes 2 to the fourth times a negative 1, which is 2 to the negative fourth power. Okay, so that would be rewriting it with the 2 as your new base. But your other option is using 4 as the base. So you take the 16 to the negative 1, and now we're replacing our base number, and we're going to make it 4 squared. And that then becomes 4 to the 2 times negative 1, which is 4 to the negative second. And these are the same number. They'll both come out to this fraction here, but it depends when we're solving these equations whether we're going to want to use 2 to the negative fourth or 4 to the negative second, which you'll see here in a second. So the steps in how to solve these equations. Your first thing is you want the bases to be the same. If they're already the same, you just get to move right into step 2. If they're not, then you need to rewrite one or maybe even both of the bases so that they match, and that's where the last example will come into play. The second step, write an equation by setting the exponents equal to one another. Then you'll solve it for your variable, and then of course you always want to check your answer just to make sure that you have done everything correctly. So here's your first example. You'll notice that the bases are 3, so the bases match. So bases match, which means we don't have any work to do with it. We just keep them as they are. So your second step is to write your equation 2x minus 1 and set that equal to x plus 2. So those, you'll notice, come from the exponents, and all we did was set those equal to one another. And then we need to solve it, so I'm going to start with subtracting x from both sides of my equation to get x minus 1 equals 2, add 1 to both sides, and you get x equals 3. And then you always want to check your answer. So 3, and then I'm going to plug in my 3 here, minus 1 equals 3 raised to the 3 plus 2. Well, this comes out to 3 to the 5th, and then this also comes out to 3 to the 5th. And there's no need to actually calculate that out because they're exactly identical as they are right now. Second example, now you'll notice that they have different bases this time. And so this is where you need to have kind of those bases memorized, and how can we rewrite so that they have the same base. Well, we know that 4 is the same as 2 squared, right? That's exactly the same thing. So what we could do is take this 4 and replace it now, and write our x minus 1, and then here's 2x plus 5, and make it 2 squared. Okay, but you'll notice we have 2 exponents here. So you'll want to write 2 and then x minus 1 like this as your exponent. So anytime that you have exponent raised to another one, you write them in parentheses like that when it's more than one to remind yourself to distribute. And now that they are the same, you're going to write an equation. 2 times x minus 1 equals x plus 5. Distribute the 2 to get 2x minus 2 equals x plus 5. Subtract x. And this will give you x minus 2 equals 5. Add 2. And we get x equals 7. And then, of course, we want to check the answer, especially because we had base changing to do. So we raise 4 to the 7 minus 1, and 7 is what we plugged in. And is that the same as 2 to the 7 plus 5? And when you actually calculate that out, this comes out to 4,096, and the other side comes out to 4,096 as well. And so we're good. And now we had to go that extra step because we actually had to change the bases, and we want to make sure that we did it correctly. The third example, you'll see we have our negative fraction here, or our fraction. So the first thing that you want to do before you start changing any bases is you want to write this as 8 to the x minus 2 and set that equal to 16 to the negative 1. So you don't want to actually work with fractions when you're solving these equations. You want to get rid of them, which I know you guys are happy about anyway. Now we have to know what base are we going to use. Well, if you look at that table, there is only one place where you will see 8 and 16. So even though 4 squared is 16, we can't have a base of 4 and get 8. So we need to use 2 cubed and 2 to the 4th. So replace the 8 and the 16 with 2 cubed and 2 to the 4th. Now this becomes 2 and then 3 to the x minus 2. They're being multiplied as one big exponent, and then same here. So this becomes 2 to the negative 4th. And now that your bases match, you write your equation. 3 times x minus 2 equals negative 4, and distribute. 3x minus 6 equals negative 4. Add 6 to get 3x equals 2. And when you divide by 3, you get x is 2/3. And then, of course, go back and plug it in. And this is something you can do in the calculator, too. It's not like you have to, do this by hand. It's an easy thing to type in and just see if they are equal. And on this side, you get 0.0625. And on this side, you get 0.0625 as well. So there you go. So that's how you decide what your bases are. And this is where it's going to come in handy to know these kind of off the top of your head and really quickly. Now that we know how to solve them, let's talk about graphing these exponential functions. And we've kind of already done these a little bit way back, when we were doing our College Board stuff. So we have this parent function where we have a base, and then x is our exponent. So exponential means that x is the exponent. So that's what makes it exponential. And they're going to look like this, and you notice that they flatten out right here. And flattening out right here means you have a horizontal asymptote. And remember that that is a line that the graph approaches but doesn't, that's an O, but does not cross. And for the parent function, it is at y equals 0, which you'll see is right here. So it gets really close, and on the calculator, it's going to look like it stops, but it doesn't. So it's really important to know that it gets close, but it does continue on forever. Now we're going to use some transformations on these things. So we've got, what's going on here. Well, the first thing is your a term, that's going to shift the y-intercept up or down. And your y-intercept is actually going to be whatever this number is right here. If it's negative, then instead of going up, it's going to go downward. All right, and then you have your b term. If your b is greater than 0, your function will be increasing, meaning it's going to look something like this the whole time. But if it's between 0 and 1, what's going to happen is it's going to be a decay, and it's going to go downward like that. The h is going to shift it left and right, and remember that's change your h. And then your k is going, you keep it, and that shifts up and down. And then this is also for the horizontal asymptote, so you use that as well. So if we're looking at this information, we have a couple things we need to find. And let's go ahead and just start with our transformations. Well, you'll notice that this is a plus 3. So we start by shifting it to the left 3 and then down 5. So instead of starting at 0, 1 right here, I'm going to go over 3 and then down 5, which starts it at -3 and then -4. So that's actually going to be our starting point. And now our y-intercept. Y-intercept is just plugging in 0 for x. So you end up getting 2 to the third, which is 8, minus 5, so you get 3. So our y-intercept is at 0, 3, which would be here. And then I'm going to go ahead and just connect it as best I can on this thing. This is going to be really hard to do. But before I flatten it out, the -5 comes from, or it has to do with your asymptote here, right there. That's your asymptote. And so when you connect it, you flatten it out at the -5, but you don't want to actually touch it or cross it. It's just really hard to do in here. Your domain is going to be all real numbers. Let's go ahead and do that, and which means it would go from -infinity to a positive infinity. And your range is going to be f of x such that f of x is greater than a -5, and that's because it's all above the -5, which would mean that it is starting from -5 and going off until infinity. And the reason we use parentheses is because of that asymptote, that it's not actually ever going to be -5. All right, now our second example, you'll notice we actually have a y-intercept here. So this is your y-intercept. Easy peasy to find. So 0, 2. That's where we start, right there. And then from here, oops, I'm sorry. Rewind. That's not, hang on. That's where our starting point is, but what we need to do is shift it. It's not going to go left or right at all, but it's going to go down 3 from the y-intercept. So here's our starting point here, but we need to go 1, 2, 3 down. And what that means then is that our y-intercept is actually 0, -1. Sorry about that. The asymptote right there, y equals -3. And this is a 1/4. The b is between 0 and 1, which means it's going to go in this direction and be more of a decay function. So we're going to cross over like this. And then, whoops, gosh, this is not easy. It needs to flatten out at the -3. This is really hard to do on this slate. I'm really sorry, guys. And then go up that way. So here's your asymptote right here. You shouldn't actually touch it or cross it. Domain is still all real numbers, -infinity to positive infinity, and then your range, g of x, such that g of x is greater than -3, which means it starts at -3 and goes until a positive infinity. All right, and then let's cruise through this last one here. The negative right here means that it is going to go downward like that. It's not shifting left or right at all, but it's shifting up 2. And so when it's negative, what is going to happen is it's going to start the intercept at a -1 and then shift it up 2 from that point. So we go up 1, 2, right there. So our y-intercept becomes 0, 1. Our asymptote is at y equals 2, which is right here. Let's see if I can make this a little bit better. There, maybe that'll work. So it's going to curve up this way and then down this way. Domain is still all real numbers, -infinity to a positive infinity, and the range h of x such that h of x is now less than 2, which would mean it's starting from -infinity and going until